So hello everyone, today we'll be discussing today's problem. Okay, if anyone is interested really in competitive programming, please join the Discord server. Hope you'll find a lot of guidance from me as well as other members here. So coming to today's problem, what does it say? What does it say? Okay, you're given a string S that contains n lowercase alphabets. There are q queries of the form L and R. Your task is to determine if every character in the range L and R can be arranged in such a manner that a palindromic substring for that range can be formed. If it is possible to create the palindrome substring in the provided interval, then print possible, otherwise print impossible. So whenever the question is something related to these kind of L and R things, so what exactly are we given? We are given a string S, we are given Q queries, and these queries are of the form L, R. Whenever the question is related to something like this L and R, it's supposed to be a range query. It's supposed to be a range query. Okay, it's supposed to be a range query, and you just need to observe. You just need to observe three basic things whenever you're basically encountering a range query kind of question. First thing, it's nature. Whether it's a static range query, like it's static is also known as offline. It's also known as offline and dynamic. This is also known as online. These are the two things you'll observe, whether it's a static range query or a dynamic range query. The third thing which you need to observe is what's the atomic operation. What's the atomic operation in this range query? Okay. So static dynamic, what does the static and dynamic mean? Static basically means like uh, after query, in between the queries, are the values changing? Are the values changing in between the queries? Like let's say there's a particular interval which was 1, 2, 3 during the first query. When Q query was 1, Q was 1, it was 1, 2, 3. By the time it was query 2, the value changed something to 1, 3, 4. If this is happening, then it's supposed to be a dynamic range query, not a static range query. In case of dynamic range queries, we use something known as a segment tree. We use something known as a segment tree. But when it comes to static range queries or offline range queries, we use prefix sum for querying. For query, we use prefix sum, and for partial sum for updating. Okay. For updating, we use prefix sum. For sorry, for querying, we use prefix sum. For updating, we use partial sum. And this is how the basic structure of range query works. And what is this atomic operation now? What is this atomic operation now? What's this atomic operation? Atomic operation is basically like what are you doing in a particular interval? What are you doing in a particular interval? An atomic operation could be maybe you're finding minimum in a particular interval, maybe you're finding maximum in a particular interval, or sum of a particular interval, which is basically the fundamental prefix sum. And maybe you're finding some sort of equal number of zeros and ones. This is a problem on lead code if you're familiar with it. Okay, you're basically might be counting something or doing anything, whatever you might be doing. That's on a query on a particular interval. It's supposed to be an, you're supposed to call it an atomic operation, not atomic query. It's atomic operation. Okay, atomic operation. Fine. It's supposed to be an atomic operation. So in this case, L to R, we need to find, what do we need to find? We need to find whether L to R is a palindrome or not. L to R is a palindrome or not. But directly we cannot just jump onto the logic, right? How do you check, forget L and R, how do you check if a string can be rearranged into a palindrome? How to check if a string is rearranged, like it can be rearranged into a palindrome? You can check it by, palindromes are of two types. The odd length ones, like this, odd length ones, or the even length ones. In case of odd length ones, basically they should be symmetric, right? One particular element can have odd frequency, one particular element can have odd frequency, rest everything should be even. B, there are two B's, there are two C's, everything is even. There could be just one with the odd frequency. When it's coming to even length, we should ensure that all of them are like even frequencies. Fine. So a palindrome can have one odd frequency character. A palindrome can have one odd frequency character, or zero odd frequency character, isn't it? It can have one frequency character or zero frequency character. If it has zero, it's an even length palindrome. If it has only one frequency character, odd frequency character, it's an odd length palindrome. Fine. We are clear about this. So does the approach boil down to something like frequency mapping? Does it? You just need to maintain frequency of every character, isn't it? You just need to maintain frequency of every character. So we figured out the atomic operation. The atomic operation is frequency mapping. Frequency mapping is the atomic operation in this case. Done with this frequency mapping. I hope everyone knows how to make frequency maps. Simple arrays, or you can use hash map too. I'll prefer using arrays. So all right. So let's make max size for this. So this says 10 power 5. That means we would need somewhere around 1e5 plus 1. Or you can take it a bit bigger number. Let's take 1e5 plus 6 maybe, anything. Okay. So let's make a, okay. Tell me one thing, what all we need to maintain. When we were doing a normal prefix sum, we had to maintain sums. Okay. We had to maintain sum, which is a zero dimension entity. It's a zero dimension entity, basically a variable. It's a zero dimension entity. 1D data structures are one dimensional entities and 2D data structures are two dimensional entities. Okay. So fine. We had to maintain a sum, which was a zero dimension entity. Now, for every range, for every L and R, in prefix sum, in general, fundamental prefix sum, we used to maintain sum. That's why we didn't require anything else. You could just do it like P of I. P of I is basically the sum from 0 to I. 0 to I. Or 0 to I minus 1, depending on how you take it. Depending on how you take it, it's 0 to I minus 1 sum. Basically, ice prefix sum. But now we have something known as a frequency of each character. Frequency of each character, you need to do it like A has some, let's say x1 frequency, B has some x2 frequency, C has some x3 frequency, so on. Okay. So isn't that very trivial? That you end up taking a 1D data structure? Isn't it? So for every range, the maximum length of the range could be till n, because in constraints it's given 10 power 5. It could be till n. And for every range, you need to maintain a 1D entity, one dimensional entity, which is frequency of the 26 characters. Okay, frequency of the 26 characters. Done. So now you would try to pre-compute it. You would try to pre-compute. What? You need to pre-compute. In these kind of prefix sum related questions, we basically do uh, the particular answer of an atomic operation in a particular range. That means you need to compute the frequency of every character in the range L to R. That means, how do I apply prefix sum here? Int n equal to s dot size, let's take for simplicity, and for int I equal to 1, I less than or equal to n, I plus plus, for int j equal to 0, j less than 26, j plus plus. And you just need to increment the value of prefix. What did we take prefix a variable? This thing. Okay. You just need to increment the value of the current character which you are at, which is obviously s of I minus 1. Okay. Since it's a lowercase letter, we subtract the ASCII value to get it. And we do a plus plus. With this, the particular character at which we are, this value would get incremented, and then we need to move to here and Copy the remaining values. Prefix sum of ij equal to prefix of I minus 1j. So with this we have copied the values. Done. The pre-compute part is done. What does pre-compute store? It stores frequency of every character from character for every L and R. Okay, we know how to query on prefix sum array. We already know how to query on prefix sum array. Okay, so basically it's the formula is prefix of R minus prefix of L minus 1, right? This is the formula which we use to query on any kind of prefix sum array. So coming to this, uh, let's write another function void solve. It to take what exactly is it taking first? It's taking the queries. Fine. So int q c in q and string s c in s, and finally we need to pre-compute for string s. We need to pre-compute the range query data structure for s. Now to answer each query, let's take the queries first. And we need to have an odd count variable. Okay, we'll iterate over like every character and find its frequency. So in frequency, let's take it f, frequency equal to prefix of what was the formula? What was the formula? You can derive it also. You can derive it also. Basically, you are getting prefix of r is giving you the prefix of like whatever is the atomic operation in between the range 0 to r minus 1, right? Isn't it? It's giving you till r. Basically, it's r plus 1 minus l, by the way. But in our case, it's r l minus 1. So this thing is giving you the atomic operation output in the range 0 to r. And if you want to make it l to r, you need to remove this part. You need to remove this part. Let's say this is l. From here, l starts. Let's say this is l. So this particular thing is l, and this particular thing would be l minus 1. So from 0 to r, you are removing 0 to l minus 1, which is giving you the interval L to R, isn't it? Isn't that very clear? Okay, so you can simply derive it. No need to like memorize some creepy stuff, and you need to track the frequency of a particular character in these ranges. Fine, this would give you the frequency of C in a particular range. If the frequency is, sorry, did I type the whole frequency? Yeah. If frequency is odd, then you'll do odd count plus plus, and okay, that's it. You'll do odd count plus plus. With this, you'll have a number of odd occurring characters, and if this odd thing is less than or equal to 1, if it's less than or equal to 1, then it's possible to make a palindrome, otherwise it's impossible to make a palindrome. Fine. If it's less than or equal to 1, it's possible to make a palindrome, otherwise it's impossible to make a palindrome. So this would print the answer for every query. Now let's test it locally before submitting. It's always good to do it. P was not declared. Okay, I guess, yeah, this is the thing. And we have this received output, which is nothing. Why did this happen? Okay, we forgot to call this solve function. Yeah. Fine. Yeah, and it passed. Okay, fine. Now we can simply submit this. It would work. It should work fine. Sample test case is passed. Let's submit this code. This is not the only way. I'll be discussing a more optimal one, and what's the intuition behind the more optimal one. Like, see, if you practice, uh, like if you are really practicing too great, then you can actually figure these kind of things out intuitively. But for someone who wants exponential growth very fast, it's basically like you need to gain as many tricks as possible so that you can actually do these kind of problems. So we discussed something about range queries. We discussed something about range queries. And whenever, remember this, whenever the search space, whenever the search space is small, whenever the search space is small, like you have some 26 characters only, right? You have some 26 characters only. And you know something that integer can store 32 bytes of information. You know that integer can store 32 bytes of information. So instead of using this huge data structure like a prefix map for each character, why can't we use something that's much smaller, like something that's uh, like an integer, right? It's a one-dimensional data structure, like two-dimensional data structure. Instead, can we use an integer? Can we? Can we do this? Yes. And this particular technique is called bit masking. It's called bit masking. Should you always do this? Should you always do this whenever the search space is small? No, you shouldn't always do this. There are peculiar scenarios where you would be trying this bit masking approach. And one of these situations is when the answer is related to something related to the odd frequencies, okay? Odd frequencies, even frequencies. When the answer is related to parity of frequencies, when you don't need the whole frequency, you just need the parity of frequency, okay? This is a peculiar case. So in these kind of cases, you'll be using something known as bit masking. Let me discuss this approach too. So basically the elimination would be done on this particular thing. What are you doing? Atomic operation never changes. All you can change is the entities. Previously, we did this using a one-dimensional entity, that's a map. We did this using a one-dimensional entity that was a frequency map. So in this whole hierarchy, can you optimize this to a zero-dimensional entity, like a single variable? This exact technique is bit masking. Okay, so I just need to, or let me rewrite the code once again. Okay, so you take the string s, c in s, and in q. Wait, first thing was the queries, right? So in q, c in q, string s, c in s, and okay, in n equal to s dot size. Let's take it this way. Or else we can do this in a pre-compute function also. You can write a simple pre-compute function, void pre-compute, just like the previous one. Void pre-compute for every string s, and you just need to create this p array once again with size n, and we have this size n this time is the same, constant n equal to 1e5. Previously we took 6, right? Yeah, this time let's don't miss the semicolon like we did previously. And coming to the pre-compute function, int n equal to s dot size, and how do you check, actually check whether a particular thing is getting correctly mapped or not? So uh, p of 0 is equal to 0. Yeah, prefix sum of I equal to prefix sum of I minus 1 XOR shift 1 to S of I minus 1 minus A. Okay, shift 1 by these many times. What does, what will it do? What will it do? Okay, let me explain what will it do. Once you're done with this, you can call this pre-compute function. You can call this pre-compute function and okay. What exactly is the pre-compute function doing? Tell me. What exactly is the pre-compute function doing? Tell me. Let's say initially this whole thing is 0. Okay, so let me do it this way. What did we do? We made a prefix array because we are still encountering range query. What did we optimize? We are optimized upon the entities. We made a one-dimensional entity into a zero-dimensional entity by using Bitmask technique. And now what are we trying to do? So prefix sum of 0 is equal to 0, which is fine. That means if I write it in the bitwise approach, it is basically like this way. And let's say I have an odd length palindrome A B C B A. Let's say I have this odd length palindrome. What are we basically trying to do? What are we basically trying to do? What exactly are you trying to do is P of I, P of I, P of I equal to P of I minus 1, which is that P of 1 would be equal to 0 XOR you're shifting 1 by these many bits. You're shifting 1 by these many bits. That means you're shifting when it's an A, you're shifting 1 by 1 bit. That means you are basically denoting A in this way. You're basically denoting A in this way. So this is A, this is a B. Okay, if I write them A, B, C, A, B, A, if I write them this way, A is denoted by 0, 0, 1, 0 because if this is 1, okay, wait, sorry, my bad. A is this thing because ASCII value of A minus ASCII value of A is 0, so it doesn't get any way shifted. And B is this thing, 0, 0, 1, 0. C is this thing, 0, 1, 0, 0. Once again, A is this thing. A is like 0, 0, 0, 1. B is 0, 0, 1, 0. 0, 0, 0, 1. And tell me something. We know that XOR is associative. XOR is associative, isn't it? XOR is associative, right? So can I say that when I XOR this A with this particular A, it would cancel out? Or else I can say that when I XOR this A with this particular A, it will cancel out. So these A's got cancelled out. And if I XOR this B with this B, will both of them cancel out? Yes. If I is it not a palindrome, I guess? A, B, C, B, A. Okay, this A doesn't exist. Let's cut it off. Fine. And C is the only thing left. Rest everything became 0. Rest everything became 0. Rest everything became a 0. So C is the only thing left. So in case of odd length palindromes, we are being left with one of this thing. What does these kind of things mean? What does these kind of things mean? One character is left. What does these kind of things mean? These kind of things mean that this is a power of 2. This is a power of 2. This is always a power of 2, isn't it? When you have all zeros, when you have all zeros and there's a 1, there's only one, and then there's again all zeros. It would be some 2 power k, isn't it? It's some 2 power k. So in case of odd length palindromes, you're getting some 2 power k as the final value. And in case of even length palindromes, what would happen? Like this one, A B B A. In this one, what would happen? A is 0 1 0 0, and B is sorry A is 0 0 0 1. B, this A is also 0 0 0 1. This B is 0 0 1 0. This B is 0 0 1 0. These A's would cancel out each other. These B's would cancel out each other. And you would end up getting a 0. So in odd length, you are getting a 2 power k. In even length, you are getting 0. This is exactly what we are gonna check. So int L, and we'll make a mask. Mask would denote basically the frequency, or what can I say? These particular values. Mask would denote these particular values. So mask basically denotes P of R XOR P of L minus 1. All right. So we'll check for if it's uh, okay. One thing could be, it could be mask could be a power of 2. How to check it's a power of 2? Mask and mask minus 1. This is how you check if it's a power of 2 or not, isn't it? You would check this is a power of 2 or not. And sorry, or either it could be a power of 2 or mask equal to 0. Mask equal to 0. And if this is the thing, it's basically possible to make it a it's basically possible to make it a palindrome. Otherwise, it's impossible to make this a palindrome. Otherwise, this is impossible to make this a palindrome. So coming to this particular property, how does this work? Let's say you have 0, 0, 1, 0, which is a power of 2, obviously. If you do a minus 1, what is this basically? This is a 2 power 1. It's 2, right? So 2 minus 1 would be equal to 1. That means this thing. All right. So basically, these two things would cancel out each other. And okay, I forgot to add the not operator. So they would end up giving you a 0, all zeros. If you want to check for even higher powers, you can check it. Okay, 0, 1, 0, 0. And let's take it, what's this? 4 minus 1, 3. So this is 0, 0, 1, 1. If you do an AND operation, this 0, 1 would cancel out, 0, 1 would cancel out, this 1, 0 would cancel out. At the end, you'll have 0, 0, 0, 0. So this is always true. And yeah, so this was it. Let's try submitting this. Before that, let's write the solve function. Solve too few arguments. So we need to it's printing always impossible. Why is it printing always impossible? Mask is giving you the, if not mask and mask minus 1, or let's keep it this way. Maybe compiler is having some sort of issue. So this one case, which is 3 to 3, 3 to 3. That means here we need to debug this once. Just wait a moment. Here everything is fine. Pre-compute is perfectly fine. So possibly this could be a reason here. Yeah, bitwise operators. Yeah, and this passed. Let's try to submit this. So once again, let's try to submit this. Hmm. Yeah, done. So there were many key takeaways from this, like range queries and atomic operations, how to optimize this by taking the bit masks, and most importantly, how does the intuition come? Like it's frequency mapping, but we are only considerate about the odd and even. We are only considerate about the parity. So this is where the intuition of bit masking comes. So that was for today, guys. Thank you, everyone.